Imagine a computer that learns like we do. It can recognize faces, understand languages, and even make decisions. These computers are not just following pre-programmed instructions. This is the promise of neural networks. They are designed to simulate the way our brains work. They are powerful tools inspired by the human brain. By mimicking our neural structures, they can perform complex tasks. Our brains have billions of neurons connected by synapses. These connections allow us to think, learn, and remember. Neural networks mimic this structure. They consist of layers of artificial neurons that process information. They have artificial neurons arranged in layers, much like a network of roads connecting cities. Each layer processes data and passes it to the next. Just as our brains learn from experiences, so do neural networks. They adjust their connections based on the data they receive. They are trained on vast amounts of data. This training helps them improve their accuracy and efficiency. This helps them recognize patterns and make predictions. The more data they process, the better they become at understanding and anticipating outcomes. Think of a neural network as a factory with different stages of production. Just like a factory, a neural network processes raw materials, in this case data, through a series of steps to create a final product. Each layer in the network represents a stage in this intricate process where data is transformed and refined. Raw materials enter the first layer, just like data enters a neural network. This initial stage is crucial as it sets the foundation for all subsequent processing. The first layer processes the data and passes it to the next layer, much like how factory workers handle materials and move them along the production line. Each layer extracts and refines information, learning more complex patterns and features as the data moves through the network. For example, in image recognition, early layers might detect edges and simple shapes, while later layers identify more complex structures and objects, such as faces or specific items. Finally, the output layer produces the final product, which could be an image classification, a prediction, or any other form of decision. This final output is the culmination of all the layers working together, transforming raw data into meaningful insights or actions. The real magic happens in the connections between neurons. These connections form a vast and intricate network that is constantly evolving and adapting. Each connection has a weight which determines its strength. These weights are crucial as they influence how signals are transmitted through the network. During training, the network adjusts these weights based on the data it receives. This process is known as learning, and it allows the network to improve its performance over time. Imagine each neuron as a tiny calculator. It performs simple mathematical operations, but when combined with millions of other neurons, it can solve incredibly complex problems. It receives signals from other neurons through the connections. These signals are like pieces of information that the neuron needs to process. The neuron multiplies each signal by its corresponding weight and adds them up. This weighted sum is then used to determine the neuron's output. If the sum exceeds a certain threshold, the neuron fires and sends a signal to other neurons. This firing mechanism is essential for the flow of information within the network. This process of weighted connections and thresholds allows the network to make complex decisions. By adjusting the weights and thresholds, the network can learn to recognize patterns, make predictions, and even perform tasks that were once thought to be the exclusive domain of human intelligence. It's important to remember that neural networks are software, not physical wires. The neurons and connections exist as lines of code in a computer program. For example, a software neuron could be represented by a simple equation. The equation would take inputs, multiply them by weights, sum them up and apply a threshold. This would determine the neuron's output. By combining millions or even billions of these software neurons, we can create powerful neural networks capable of solving complex problems. From self-driving cars to medical diagnosis, the possibilities are endless.